Assalamu alaikum. Today I want to talk about chapter 13, part 1, properties of solutions. Now, 13.4, expressing solution concentration. Now, the concentration of a solution can be expressed either qualitatively or quantitatively. The terms dilute and concentrated are used to describe a solution qualitatively. A solution with a relatively small concentration of solute is said to be dilute. One with a large concentration is said to be concentrated. Now, chemists use various ways to express concentration quantitatively, and we examine several of these next. Mass percentage. One of the simplest quantitative expressions of concentration is the mass percentage of a component in a solution is given by mass percent of A equal mass of A in solution divided by total mass of solution times 100. Now, where we have abbreviated solution as percent means per 100, thus a solution of hydrochloric acid that is 36% HCl by mass contains 36 grams of HCl for each 100 gram solution. We often express the concentrations of very dilute solution in parts per million and parts per billion. As you can see here, parts per million. These quantities are similar to mass percentage but use 10 to the 6 million or 10 to the 9 billion respectively in place of 100 as a multiplier for the ratio of the mass of solute to the mass of solution. Thus, parts per million is defined as ppm of component equal mass of A in solution divided by total mass of A of solution times 10 to the 6. A solution whose solute concentration is 1 ppm contains 1 gram of solute for each million grams of solution, or equivalently 1 milligram of solute per kilogram of solution. Because the density of water is 1 gram per ml, 1 kilogram of a dilute aqueous solution will have a volume very close to 1 liter. Thus, 1 ppm also corresponds to 1 milligram of solute per liter of aqueous solution. Now, the acceptable maximum concentrations of toxic or carcinogenic substances in the environment are often expressed in ppm or ppm, parts per billion. For example, the maximum allowable concentration of arsenic in drinking water in the United States is 0.010 ppm. That is 0.010 milligram of arsenic per liter of water. This concentration corresponds to 10 parts per billion. Let's look at this sample exercise. Calculation of mass-related concentrations. Now, a solution is made by dissolving 13.5 grams of glucose in 0.100 kilogram of water. What is the mass percentage of solute in this solution? So mass percent of glucose. Mass of glucose divided by mass of solution times 100. So 13.5 divided by 13.5 gram plus 100 gram of water times 100, it's 11.9%. So the mass percentage of water in this solution is 100 minus 11.9%, and this equals 88.1%. Then this is mass percent of solute, this is mass percent of solvent. B is a 2.5 gram sample of groundwater was found to contain 5.4 microgram of zinc plus 2. What is the concentration of zinc plus 2 in parts per million? Now, لاحظوا, in this case, we are given the number of microgram of solute because 1 microgram is 1 times 10 to the 6 gram. 5.4 microgram equal 5.4 times 10 to the minus 6 gram. We calculate the parts per million using the previous equation, and we solve ppm equal mass of solute على mass of solution times 10 to the 6, and then we will get this 2.2 ppm. You can solve the practice exercise below, which is similar to what we have talked about in this sample exercise. After that, we go to another way of expressing concentration, mole fraction. Concentration expressions are often based on the number of moles of one or more components of the solution. Recall from section that the mole fraction of a component of a solution is given by this: x of A equal moles of A divided by total moles in solution. Now the symbol X is commonly used for mole fraction with the subscript to indicate the component of interest. Okay. In some application, one needs the mole fraction of solvent, not solute. Make sure you find the quantity you need. Then we have molarity. Recall from section 4.5 that the molarity of a solute in a solution is defined as molarity equal moles of solute per liter of solution. For example, if you dissolve 0.500 mole of Na2CO3 in enough water to form 0.250 liter of solution, then the solution has a concentration of 0.5 divided by 0.25, and this is equal to 2.00 molar in Na2CO3. Since volume is temperature dependent, molarity can change with temperature. Molarity is especially useful for relating the volume of a solution to the quantity of solute it contains, and it is, as you can see, temperature dependent because the volume will change with the temperature. Then we have the molality. The molality of a solution, denoted small m, is a unit that we have not encountered in previous chapters. This concentration unit equals the number of moles of solute per kilogram of solvent. Thus, if you form a solution by mixing 0.2 mole of NaOH, 80 gram, and 0.5 kilogram of water, 500 gram, the concentration of the solution is 0.2 divided by 0.5. This equals 0.400 molal. We call it molal in NaOH. Since both moles and mass do not change with temperature, molality, unlike molarity, is not temperature dependent. Look at this sample exercise: calculation of mole fraction and molality. An aqueous solution of hydrochloric acid contains 36% HCl by mass. A. Calculate the mole fraction of HCl in the solution, and B. Calculate the molality of HCl in the solution. So here, if to solve مثلا A, to calculate the mole fraction of HCl, we convert the masses of HCl and H2O to moles. Moles of HCl equal 36 divided by the molar mass of HCl, 36.5, and this is the number, 0.99 mole HCl. Moles of water, 64 divided by 18, the molar mass of water, equal 3.6 mole of water. Now, mole fraction X of HCl equal moles of HCl divided by total number of moles, 0.99 divided by 3.6 plus 0.99, and the mole fraction of HCl will be 0.22, as you can see here. Now, to calculate the molality of HCl in the solution, we calculated the number of moles of HCl. Then molality by definition equal moles of solute divided by the mass of solvent in kilogram. Okay, 64 gram equal 0.064 kilogram, and the molality is 15 molar. Now, changing molarity to molality. Now, to interconvert molality and molarity, we need to know the density of the solution. So in this figure outlines the calculation of the molarity and molality of a solution from the mass of solute and the mass of solvent. The mass of the solution is the sum of masses of the solvent and solute. The volume of the solution can be calculated from its mass and density. This figure shows us calculating molality and molarity from solute mass, solvent mass, and solution density, and you can follow this to calculate molarity, and if we know the density of the solution, we can calculate the molality from the molarity and vice versa. Let's look at this sample exercise. Calculation of molality using the density of a solution. A solution with a density 0.876 gram per ml contains 5 gram of toluene and 2 to 5 gram of benzene. Calculate the molarity of the solution. So this is the plan. So first we find the number of moles of solute here, 5 divided by 92, the molar mass of toluene. This is moles of toluene, 0.054 mole. The density of the solution is used to convert the mass of the solution to its volume. Then milliliter of solution equal 230 grams times 1 divided by this density, and we have 263 ml. Then molarity in moles of solute per liter of solution. We have the moles and we have the solution. We convert it to liter and we have molarity equals 0.21. Now check the magnitude of our answer is reasonable. Rounding moles of 0.05 and liters to 0.25 gives a molarity of this amount. Now, the units for our answer are correct, moles per liter, and the answer 0.21 molar has two significant figures corresponding to the number of significant figures in the mass of solute, which is this 5.0. Now let's talk about 13.5 colligative properties. These properties, these are physical properties of solution that depend on the quantity or concentration, but not the kind or identity of the solute particles. They are called colligative. Colligative means depending on the collection. Colligative properties depend on the collective effect of the number of solute particles. So we have among colligative properties are vapor pressure lowering, boiling point elevation, melting point depression, and osmotic pressure. So we are going to examine each of these. But notice how the concentration of the solute affects the property relative to that of the pure solvent. Let's start with vapor pressure lowering. Because of solute-solvent intermolecular attraction, higher concentrations of non-volatile solutes make it harder for solvent to escape to the vapor phase. Now this figure shows us vapor pressure lowering. The presence of non-volatile solute particles in a liquid solvent results in a reduction of the vapor pressure above the liquid. So, a substance that has no measurable vapor pressure is non-volatile, whereas one that exhibits a vapor pressure is volatile. Now we are to compare the vapor pressures of various solvents with those of their solutions. We find that adding a non-volatile solute to a solvent always lowers the vapor pressure. As you can see in this figure, the vapor pressure over a solution formed by a volatile solvent and a non-volatile solute, here one, and here we see is lower than that of the solvent alone, like this. The extent of the decrease of the vapor pressure upon addition of the solute depends on the concentration of the solute. Now, the extent to which the non-volatile solute lowers the vapor pressure is proportional to its concentration, and this relationship is expressed by the so-called Raoult law. And then again here the vapor pressure of a solution is lower than that of a pure solvent. And then again Raoult's law, which states that the partial pressure exerted by a solvent above a solution P of A equals the product of the mole fraction of the solvent in the solution X of A times the vapor pressure of the pure solvent P naught of A. As you can see here, for example, the vapor pressure of water is 17.5 torr at 20 degrees centigrade. Imagine holding the temperature constant while adding glucose to the water so that the resulting solution has X mole fraction of water is 0.800 and that of glucose is 0.200. According to this equation, the vapor pressure of water over the solution will be 80% of that of pure water. So P of water equal 0.8 times 17.5 and is equal 14 torr. Now, in other words, the presence of the non-volatile solute lowers the vapor pressure of the volatile solvent by about, in this example, 3.5 torr. Now, this Raoult's law predicts that when we increase the mole fraction of non-volatile solute particles in a solution, the vapor pressure over the solution will be reduced. In fact, the reduction in vapor pressure depends on the total concentration of solute particles, regardless of whether they are molecules or ions. Remember that vapor pressure lowering is a colligative property, so it depends on the concentration of solute particles and not on their kind. And here we have a note. This is one of those times when you want to make sure you have the vapor pressure of the solvent. Let's see this sample exercise about calculation of vapor pressure lowering. We have this glycerin is a non-volatile non-electron with the density equal at 25. Calculate the vapor pressure at 25 of a solution made by adding 50 ml of glycerin to 500 ml of water. The vapor pressure of pure water at 25 is 23.8 torr and its density is 1 gram per ml. So our goal to calculate the vapor pressure of a solution given the volumes of solute and solvent and density. So here to calculate the mole fraction of water in solution, we must determine the number of moles of glycerin and water. Moles of glycerin, 50 times the density, and then divide by the molar mass of glycerin. It's 0.684 mole. Moles of water, 500 times 1 divided by 18, 27.8 mole. So we now use Raoult's law to calculate the vapor pressure of water for the solution. X of water equal moles of water على total moles, and it's equal 0.976. Vapor pressure of water equal mole fraction of water times the vapor pressure of pure water, the one we are given here. So it is 23.2 torr. Now the vapor pressure of the solution has been lowered by 0.6 torr relative to that of pure water. Thank you. End of part 1.